Good morning, children. So the next topic is clock rule. Now we have seen that when the magnetic field is passing through a circular loop of current, then depending of the direction of current, the direction of the magnetic field we have to decide. So there is an interesting rule which is named as clock rule. We can decide that what will be the direction of the magnetic field depending on the direction of the current in the loop. So you please draw the diagram along with me according to the instruction given. So first of all, what you do, you make two circles. Alright, first you make two circles. Clear? Then you see here you draw two vertical arc. And here you draw two horizontal arc. Alright. So you see what you have to do, that in one circle you draw two vertical arc. And in one circle you draw two horizontal arc. Is that clear? Now you see. Here you join the upper end and lower end of the two vertical arc. Is that clear? And here you join the upper end and lower end of the two horizontal arc. Clear? Then here at the free end of the two arcs drawn, put an arrow. And then here also at the free end of the two arcs drawn, put an arrow. Then outside the along the circle, how to draw the arrow? Just like the arrow you have drawn at the free end. You see here, the arrow is in this direction. So, draw the arrow. Here also, do the same. That you draw the arrows like this. Okay. So, this is the way you have to draw the diagram for the clock rule. Alright. Clear to everyone? Now is coming the interpretation part. So, you look at the first diagram. You see, inside the circle, what you have got? You have got an N. Alright. And you see in the circle, in which direction? This is the circular loop actually. In the circle, in which direction the current is flowing? You see, look at the diagram. It is current is flowing in the anti-clockwise direction. Alright. Then, how the loop will behave? The loop will behave like a north pole. Alright, now look at the second diagram. In the circle, how the current is flowing? The current is flowing in the clockwise direction. Alright, so the current is flowing in the clockwise direction. And look at the circle, what you have got? You have got an S. What does it mean? It will behave like a south pole. So, this is the way one can remember the clock rule. That when current is moving in the anti-clockwise direction, the loop will behave like a north pole. And when current is moving in the clockwise direction, the loop will behave like a south pole. The next topic is magnetic field due to a current carrying solenoid. So first of all, you have to know what is a solenoid. Alright, solenoid is a cylindrical loop of coil whose length is much greater than its diameter. Alright, so what is a solenoid? Solenoid is a current carrying loop cylindrical coil. Alright, means just you consider, suppose you have wrapped several loops turned on this one. Okay, on this one, then what you will get? You will get a cylindrical coil. Now, the cylindrical coil here, one restriction is there. What? That length of the coil should be much higher than the diameter of the circular coil. Okay, or diameter of the loop. That is known as the solenoid. Alright. Now, suppose you have taken a solenoid. So, here you see I have tried to draw the diagram by the black color. So, you have taken, you see the circular loop like this. So, how you have taken the turn? You see the turn you have taken from front to back like this. Means you see you can take the turn like this also. You can take the turn like this also. So, here how the turn is taken from front to back. Alright, so from front to back the turns are there. Then the two ends, they are connected to a battery, key and rheostat. Battery, rheostat and key in series. And then again here on the means suppose this is the circular loop, here the cardboard is, and you have spread the iron filings, then you will see that iron filings again, it will place themselves along the direction of the magnetic field. Then what will be your observation? That iron filings, they are placing like this. The blue color dotted line I have drawn, that are the magnetic field lines. Alright. Now, if you observe the magnetic field lines here, just you see, look at inside the solenoid, at the center of the solenoid. At the center of the solenoid, the lines are parallel to each other. At the end, they are diverging. But what about within the solenoid? Within the solenoid, the magnetic field lines are parallel to each other. So, what is the first conclusion you must write? That near the center of the solenoid, the magnetic field is constant. So, what is the first conclusion you have to write? Near the center of the solenoid, magnetic field is constant and uniform. Then, second observation. If you consider outside the solenoid, you see outside the solenoid, here is one line, here is one line. Just look at the gap. What does it indicate? Magnetic field is almost zero outside the solenoid. What is the second conclusion? Magnetic field is almost zero outside the solenoid. So when current passes through a solenoid, where the magnetic field is produced? Within the solenoid. But outside the solenoid, magnetic field is almost zero. Alright, and within the solenoid, what kind of magnetic field is produced? Magnetic field is produced uniform or constant. Clear to everyone? I repeat the first point, magnetic field near the center of the solenoid within the solenoid is constant. Then second point, magnetic field outside the solenoid is zero. Alright, then next is if you increase the magnitude of the current by the rheostat, then you will observe that concentration of the lines of force increases. What does it mean? Magnetic field, it depends on the current passing through the solenoid. Alright, if current passing through the solenoid increases, magnetic field increases, vice versa. What is the next point I said? I am repeating it, that magnetic field depends on the current passing through the solenoid. If the current increases, magnetic field increases and vice versa. The next point, if you increase the number of turns, here you see I have taken 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 number of turns I have taken. Instead of 9, if you take it 15, 20, means if you increase the number of turns, then you will observe the magnetic field also increases. So what is the next point you have to remember? Magnetic field depends on the number of turns of the solenoid. If the number of turns of the solenoid increases, magnetic field increases and vice versa. Is that clear? Clear to everyone? I hope so. Then, magnetic field produced by the solenoid depends on another point. It depends on the material kept as a core of the solenoid. Alright, what is core? Just you consider, suppose this is the turns of the loop. So here, this portion, it is known as the core. So inside the core, you may have air, or you may use soft iron, you may use any other material. Alright, so here when you are using any other material just like soft iron, then what will happen? Soft iron, due to the certain important property, magnetic permeability of soft iron is much more higher. So you will observe that magnetic field produced by the solenoid increases. So magnetic field produced by a solenoid depends on three factors. Magnetic field produced by a solenoid depends on three factors. First factor, current. If current through the solenoid, if current increases, magnetic field increases, vice versa. Second point, if number of turns of the magnetic field number of turns of the solenoid increases, magnetic field increases, vice versa. Third point, material of the core used within the solenoid. Alright, depending on the magnetic property of the core, magnetic field changes. If you use soft iron, then magnetic field becomes maximum. Okay, so if you use air, then what will happen? Relatively less amount of magnetic field will be produced. But if you use soft iron as a core, then magnetic field strength of the magnetic field increases. So depending on the material of the core, magnetic field varies. Alright, if you use soft iron, magnetic field will increase. If you use air core, AIR, air core, then what will happen? Magnetic field will decrease. Clear? So next one is about the direction. Now regarding the direction, I'll teach you how to find out. You just hold a pen or pencil like this in front of your eye. Okay, just like this. You see how I am holding it? Perpendicular to my eye. How I am holding it? Perpendicular to my eye. Then you place one finger along the direction of the current. So if you consider this diagram, you see the current is from front to back. So you see how I am placing my finger from front to back. I am turning my finger front to back. Now you look at it perpendicularly. So if I look at it perpendicularly, in which direction I am seeing the loop? It is in the anti-clockwise direction. So anti-clockwise direction means which kind of pole will be produced at one end? North pole. And here, if you consider the direction of the current, then you will see here south pole will be produced. So it is my advice that this kind of conceptual question you will get rather in the sample question paper that is sent from the council. This kind of question is there, that depending on the direction you have to find out what is the polarity at the two end of the solenoid. Okay, so how to find out? Apply this rule, that if you just hold the pen or pencil in front of your eye, perpendicular to your eye, then set your finger on this side, on the left side, along the direction of the current. So if it is front to back, it will be like this. And when you are holding it like this, then you see the current is in the anti-clockwise direction. So north pole will be produced here. So once you decide which pole is produced to the left side, automatically the opposite one will be produced at the right side. Now you see here, if I hold this one and if I set my finger like this, means if you change the direction of the current from back to front, then you see if I set my finger like this, then the current is appearing in the clockwise direction. So if the current is in the clockwise direction, then it will become south pole and it will become north pole. Alright, so what we are observing, another important point we are observing, that a current carrying solenoid behaves like a magnetic dipole, behaves like a bar magnet. It is very important. How does a current carrying solenoid behaves? Current carrying solenoid behaves like a bar magnet. And you know that if once a bar magnet suspended freely, then always the bar magnet set itself along the geographic north-south direction. So like that, if a current carrying solenoid suspended freely, how it will set itself? It will set itself along the geographic north-south direction, because a current carrying solenoid behaves like a bar magnet, and the magnetic field, that's why the lines of force due to a current carrying solenoid, it looks like a bar magnet's magnetic field. Okay, so this is the next point you have to remember. So another point you have to remember regarding the solenoid is that if you change the direction of current in the solenoid, if you reverse the direction of current in the solenoid, then magnetic field get reversed. Alright, so that's all about the magnetic field due to a current carrying solenoid.